This is an example video of conservation of angular momentum, walking on the merry-go-round. Here's the problem we're going to be working with. A 150 kilogram, 1.5 meter radius merry-go-round disc is turning at 2 revolutions per second with a 50 kilogram passenger standing at the very center. If the passenger walks carefully to the very outer edge, what will the rotation rate of the merry-go-round be once she gets there? Assume the passenger walks in a straight line and the merry-go-round has frictionless bearings. I recognize this problem. This is a conservation of angular momentum problem. Some of the clues that it's angular momentum are, of course, that it's rotating. Also, enough information is given that I know I'm talking about angular speed, and there's enough information that I can calculate moments of inertia, which are, of course, very important for angular momentum. So I've drawn sketches of before and after. The event that separates these is the walk from the center of the merry-go-round out to the outer edge. So a conservation of angular momentum problem, I'm going to set the initial angular momentum equal to the final angular momentum. The initial angular momentum, I will consider the moment of inertia of each object, so the disk, and multiply that by the rotation of the disk, which is omega initial. And then to be complete, I should add to that the moment of inertia of the passenger times the passenger's angular speed. The disk and the passenger move together. They have the same omega initial. This will be equal to the moment of inertia of the disk times its final angular speed plus the moment of inertia of the passenger in the final case times that passenger's final omega f. So the initial moment of inertia of the passenger, since the passenger is described as being at the very center of the merry-go-round, then we have a choice to make. The passenger is not quite a point that's all at the center, but compared to the disk, the passenger is less massive and has a much smaller radius. And so I am going to choose to make the passenger's initial moment of inertia equal to 0, which will cancel out this entire term to be 0. That leaves the initial moment of inertia to be the moment of inertia of the disk times the initial angular speed. And then finally, the disk and the passenger are going to rotate at the same angular final speed. And so we will just need to calculate the sum of the final moment of inertia of the disk, should be the same as the initial moment of inertia of the disk. Add to that the passenger's moment of inertia in the final case. Since the passenger is not at a radius of 0 anymore, finally, then that's not going to be 0. Let's consider some of the numerical values. So the moment of inertia of the disk, you can look this up. This is 1/2 times the mass of the disk times the radius of the disk squared. In this case, that's going to be equal to the 1/2 times 150 kilograms times the radius of the disk, that was 1.5 meters. We will square that. So the moment of inertia of the disk, oh, I forgot my subscript, of the disk here is going to be 168.75 kilograms meters squared. Now, the initial angular speed, we were told it was 2.0 revolutions per second. Now, it's going to turn out that we could leave this speed in terms of revolutions per second, but our standard unit for angular speed is radians per second, and just for practice, I'm going to go ahead and convert this. So 1 revolution is the same as a full circle, which is 2 pi radians, and so omega initial is also equal to 4 pi, So that's 2 times 2 pi, and now this is radians per second. So I know that the initial moment of inertia is 168.75 kilograms times meters squared times 4 pi radians per second. And all that is going to be equal to the same moment of inertia of the disk, but this time add to it the moment of inertia of the passenger times omega final, which is what I'm solving for. So we've already calculated that the moment of inertia of the disk was 168.75 kilograms meters squared. Now we need to find the moment of inertia of the person in the final case, when the person is at the very edge. We are going to model this person as a point mass when they reach the edge of the merry-go-round. And so they will have a moment of inertia of their mass times their distance from the center of rotation squared. So this will be equal to 50 kilograms times the 1.5 meters to the very edge squared. And so this moment of inertia of the person is equal to 112.5 kilograms meters squared. So now if I put this together, I have 168.75, the original moment of inertia of the disk, times the original angular speed of the disk, which was 4 pi radians per second. I'm going to set that equal to, I have the sum of the disk moment of inertia plus the passenger moment of inertia, and that together is equal to 281.25 kilograms meters squared, and multiply that by omega final, which is what I'm trying to discover. So let's take our final algebra steps. I'm going to divide both sides by 281.25 kilogram meters second squared. Sorry, kilograms times meters squared. And that's going to give me 0.6. The units have canceled out, times 4 pi radians per second equals omega final. So omega final works out to be 2.4 times pi radians per second. That's a perfectly good answer. We could stop there, or we could take it back to revolutions per second, which were the original units of angular speed that we were given. And so again, there are 2 pi radians in 1 revolution, and so this works out to be an omega final of 1.2 revolutions per second. And that's my final answer. The merry-go-round did slow down as the person walked to the outer edge, and when you consider that the moment of inertia increased, then it makes sense that the angular speed has to decrease in order to keep the same overall angular momentum.